Hi everybody, and welcome to our module on correlations. We'll start by talking about the correlation coefficient, also known as the Pearson coefficient. And to understand this, let's imagine we were going to examine the relationship between pack years of smoking and lifespan. Now, because we know smoking is bad for you, we would expect that individuals who have lots of pack years of smoking would have a shorter lifespan, something like what I'm marking with my pen here. And individuals who have smoked very little would have a longer lifespan, something like up here. And then in the middle, we would have individuals who have smoked a medium amount, and they would have a lifespan something like this. Now, if the only thing that determined lifespan was pack years of smoking, if nothing else mattered, then the relationship between pack years of smoking and lifespan would look something like this. It would essentially be a straight line. But in reality, many things contribute to lifespan, not just smoking. So the actual relationship between pack years of smoking and lifespan looks more like this. There's scatter in the data because some individuals who have smoked a lot still manage to live somewhat longer lives, and some individuals who have not smoked much still live somewhat shorter lives, and that's because other things besides smoking affect lifespan. Smoking is just one factor, but there are many others. So a correlation coefficient attempts to describe the relationship between smoking and lifespan, and to describe how much of lifespan is associated with pack years of smoking. And the way you calculate a correlation coefficient is by fitting a line through the data that are shown on the slide like this. This line is mathematically calculated to minimize the distance between all the points on the graph and the line. And so what we're going to talk about in the next few slides are the characteristics of this best fit line through the data. Those are used to determine the correlation coefficient, which describes the relationship between a variable like smoking and an outcome like lifespan. So the correlation coefficient is a measure of the linear correlation between two variables, and it represents the strength of association between the two variables. I'll explain what this means in a minute. It's a number that ranges from -1 to +1, and it's derived from that best fit line we saw on the last slide. The closer the number is to 1, the stronger the relationship. And if the correlation coefficient is negative, it means there's an inverse relationship, like what we saw for smoking. With more smoking, there was less lifespan. If the correlation coefficient is a positive number, that means there's a positive relationship, such as more smoking means more lifespan, which of course is not the situation in reality. And then if the correlation coefficient is 0, this means there's no relationship between the two variables. So let's talk about how the correlation coefficient describes the strength of a relationship between two variables. The correlation coefficient is denoted by a lowercase r. And in these data on the left, the best fit line through the data has a correlation coefficient of +0.5. It's positive, meaning the relationship is positive. As you get more of the variable on the x-axis, you have more of the variable on the y-axis. But the value is 0.5 and not closer to 1. And the reason that's the case is because, as you can see, there's lots of scatter in the data. An r value of +0.5 represents a relatively weak relationship between the two variables. In contrast, if you look on the right, once again we have a positive r value indicating a positive relationship between the two variables. But in this case, the r value is 0.9, and that's because there's much less scatter in the data. All the data points are much closer to the best fit line. That means there's a stronger relationship between the two variables, and therefore the r value is also going to be closer to 1. Besides telling you the strength of relationship, the correlation coefficient tells you about the direction of the relationship. So on the left is a data set where the r value is -0.5. The correlation coefficient is a negative number, meaning there's an inverse relationship between the two variables. The more you get of the variable on the x-axis, the less you have of the variable on the y-axis. This is what smoking versus lifespan would look like, as we talked about earlier. In the middle, we have a positive r value of +0.5, which means the more you get of the x-axis variable, the more you get of the y-axis variable. This is what the relationship between something like exercise and lifespan might look like. And then on the right side of the screen is an r equal to 0. There's no relationship. The best fit line is a horizontal line like this, indicating no relationship between the variable on the x-axis and the variable on the y-axis. So the reason you need to understand the correlation coefficient is because many studies report relationships with this correlation coefficient number. For example, imagine a study was conducted of pneumonia patients, and the researchers examined the relationship between the white blood cell count on admission and the length of stay for treatment of pneumonia. They might report an R value of +0.5. It's a positive number, so it means the higher the white blood cell count, the higher the length of stay. but the value is only 0.5, meaning the white blood cell count at admission only explains some of the length of stay. There are other variables that are also very important. And sometimes studies will also report a p-value along with the correlation coefficient. A p less than 0.5 indicates a significant correlation between the two variables. A p greater than 0.5 indicates no significant correlation. But the p-value only tells you whether the relationship is statistically significant. It doesn't tell you anything about the direction or the strength of the relationship. That's why the R value is helpful. Sometimes instead of a correlation coefficient, a related number will be reported called the coefficient of determination. This is also referred to as the R squared. It's called the R squared because it represents the square of the R value. And so because you're squaring the R value, the R squared is always positive. Whether the R is positive or negative, you will always get a positive value for R squared. And the reason study authors like to report the R squared is because it represents the percent of variation in the Y variable that's explained by the X variable. If you look at this data set on the bottom left side of the screen here, the R squared value is 0.6. What that means is that 60% of the variation in the Y variable here is explained by variability in the X variable shown here. So if we were talking about our pneumonia study again and length of stay were the Y variable, this would say that 60% of the variability in length of stay is explained by changes in the white blood cell count on admission. The remaining 40% of the variability in length of stay is explained by other measures. Shown on the right is a hypothetical example where the R squared is equal to 1. Situations like this are very rare in studies, but if you ever find one, it means that 100% of the variation in the Y variable is explained by variation in the X variable. And so because the R squared indicates the percent variation of Y explained by X, it's a very easy to understand number, and it's often presented in clinical studies. And that concludes our module on correlations.